So for drivers, there are quite a few different attack surfaces depending on the purpose and type of the driver. Um, so I'm just going to briefly cover it here. We're not going to go and do a detailed examination of a driver just yet. I'm going to leave that for a bit later where we actually will reverse engineer a driver. We'll write our own code to interact with a driver. We'll even write our own driver, and we'll go through a logic 0-day bug in a current driver, and we'll write some nice code to get through some of its self protection mechanisms that are faulty, such that we can get around them. But we'll dive into that more in later sections. I'll just give a brief overview that drivers can interact with userland. So drivers get loaded into the kernel and they work with the kernel APIs, but they can interact with userland if they wish using a few different mechanisms. A common one is what's called as a IO control handler or an ioctl handler, where a userland process can get a handle to a driver by opening up as a file in the object namespace slash device slash and then the device name. And that is a common cause of bugs where the driver mishandles user input in some fashion. Some kernel drivers are actually meant, like they're designed to get around security, such that they might, a company might release a driver that can read and write physical memory. And because as userland processes don't have that ability to read and write physical memory because of security, we have virtual memory isolation. They'll expose a driver that anyone can access that gives them the power to read and write physical memory. Now that can be abused by malware to read and write memory of any process or anywhere in the kernel on the system. And that can be used for privilege escalation. It can be used for evasion. It can be used to um, get rid of or disable security software like EDRs and things like that. And then other types of drivers are just buggy. They have, buffer overflows, use after freeze, all that sort of thing. But there's more ways to interact with a driver than just via ioctls. Drivers can get notified and pass user input when you do certain operations, such as open files, open process handles, and all sorts of operations that the Windows kernel supports, notifying drivers of when those operations happen. So you can be aware of it enough for now. We'll definitely go into much more detail and work with these in later sections. Other common kernel bug classes that are worth mentioning even at this point focus around concurrency issues and reference counting. So when it comes to userland code, um, processes like global memory is restricted to that process usually, right? For example, let me bring up uh, draw.io. Yeah. Okay, consider the scenario where you have. Let me change the background. Okay, so consider the scenario where we have two processes. Proc1 and proc2. Proc1 has a global, global int my global, and say proc2 has something similar. Whoops. Say proc2 is something similar. Okay, they're globals, but these processes, right? Unless you have something mapped as shared memory, by default, they do not have access to each other's memory space. Meaning, if proc1 writes and reads from its global here, that does not affect proc2's global, right? They're separated in different virtual memory spaces. They have different page tables. In the kernel, That's not usually the case. By default, you're loaded up into the kernel address space. So if you have, my kernel driver, and this has a global, um, global int my global, it's going to be at a certain address. Let's say FFFF 8200. So we load up our driver in kernel space. It has a global int called myGlobal. And when it's actually loaded into kernel, it gets this address, FFFF8200, as an example. Now say there's some other driver, right? It's not our driver, it's just some other driver. If it goes to write to FFFF8200, if it goes to write to this address, if these were two userland processes, the write to this address would be in its own virtual memory space that's separate from ours, so it would not write to our global, right? Because we have different page tables. But by default, when drivers are loaded into the kernel, they share the same page tables, they share the same CR3. So when some other driver writes to this address, it's going to be writing to the global that's used by our driver. Essentially, by default, all kernel memory is shared memory between everything in the kernel. Now, there's nothing stopping a kernel driver from creating its own page tables and setting its CR3 to its own created page tables such that it can have like essentially private memory, right? That's separate from the address space of any other kernel object. But the driver would have to intentionally do that. By default, it's just all shared memory in kernel land, essentially. And this means that since a lot of these things are shared and drivers can be entered multiple times by userland code, take, for example, we have a driver that writes and reads to this global, and this driver accepts input from userland. Say we have proc1, shrink this, we have proc2, we have proc3. If all of them fall into the driver at the same time, and I'm going to assume we're running on a machine that has at least 3 logical CPUs, it's possible that these 3 threads are executing at the same time inside the driver. And if all of the 3 threads at the same time are reading and writing to the same spot in memory, such as a global, you can have race condition type bugs, concurrency issues, where maybe proc2 triggered the driver to overwrite my global. But while proc2 is writing to my global, say it writes it halfway, and before it can finish off the rest of the write, proc1 reads the global. And then proc3 also reads it. You have the case where because of proc2's write not happening atomically in a single CPU cycle, and there's no locking mechanisms in this example, that proc1 and proc3 get malformed data from reading the global because it was being written to at the same time it was being read from. So there's lots of like concurrency type issues like this in kernel drivers that you'll find in those types of bug classes that are a little bit less common in user code as it is in kernel code. But user code can have this problem as well when there's multi-thread processes operating on like global structures without using either locks like mutexes and spin locks for the kernel, or without using atomic operations, which are guaranteed by hardware to happen in like a single CPU cycle such that there won't be any partial writes. So we don't have to worry about reading malformed data. But this is a common issue. Same with reference counting, which leads to use after free. Reference counting, I'm just referring to things like where kernel code will keep track of the lifetime of an object based on its reference count, but there can be bugs where something is freed or allocated and it goes through a path where the reference count isn't properly updated to reflect that allocation or free. And since the reference count becomes invalid, it could hit 0 prematurely, leading to freeing an object that still has pointers to it, leading to a use after free, and things like that. Then, since kernel code can accept pointers and data from user code, from user land, you have bugs where the kernel code does not properly check that a user provided pointer actually points to user memory and not somewhere in the kernel. It's not a kernel pointer. And there's APIs in Windows to support this check with probe for user. No, it's probe for read and probe for write. If I search for probe for read MSDN, you'll see the probe for read function. There's also probe for write. And you'll see a lot of these used in the kernel when they take a userland pointer and they want to verify that it resides in userland address space and is correctly aligned. You also have issues where, like double fetch issues. And double fetch is kind of related to concurrency. It's where you have, say, we have our driver and we got our process. Say one thread of the process calls into the driver and passes through a pointer that points to 7FFF100, right? Points to here. My driver, say it reads from the pointer, and then say it does some checks. Maybe this pointer is supposed to contain a path to somewhere to write. So it reads it, it validates that it's a valid path. So maybe this pointer contains the value C drive users my user documents. And maybe this function call into the driver is telling the driver to delete a folder. And this is a bit of a odd example because like you can just delete the driver from user. But for the sake of this example, say this pointer is a string pointer pointing to the path where we want to delete. So the driver gets that pointer, it reads the pointer and sees the value is C drive users my user documents. Maybe this check is a check to see if does user have permissions to delete. Maybe the check goes and sees if proc1, if the proc1 process token belongs to a user that have or has permissions to delete this folder. If yes, then it goes down, and then it's like, actually, maybe I should do this. Does it have permissions? If yes, it has permissions, then it goes down here. And then now, read pointer again. And delete folder. Okay. So proc1 passes through a pointer to the driver. The driver reads the string from the pointer and it passes it to a check function. The check function, or maybe it gets a pointer, and instead of reading from that pointer straight away, perhaps it passes that pointer to a check function. That check function reads the pointer, sees it's this string, checks if the process has delete permissions on that folder. If yes, goes back to the main driver code. The main driver code then passes through that pointer to a delete function. Can you identify the bug here? So in this case, proc1 has a thread running in the driver doing these things. But what if there was another thread running that changed the pointer contents to try and beat a race condition and modify it after this second point? What I mean by that is, say we have one thread calls into the driver, it goes into the check functionality, the check sees this string from the pointer, sees if the process has permission to delete it. If yes, goes back, tells the driver, yes, process can delete the string in this pointer. My driver passes through that pointer to a delete function, and that delete function dereferences that pointer again to get the string from it again and delete it. What about if between this first check and this second read, proc1 has another thread here that changes the pointer value or the pointer contents to contain a different string, such as C drive, Windows, System32, where it would not have permissions to delete. Well, the check function, when it checked the contents of that pointer, it contained the documents string and it saw it had permissions. But since this pointer is being dereferenced again for a second time, when it goes to delete the folder, and proc1 has another thread that will race this operation to write to that pointer and change it to somewhere else, it's possible that when it goes to delete folder, that pointer now contains a different value than the one that was checked. This is referenced as a double fetch bug, where the data from user is fetched twice or more than once. The best practices for this usually is to read the user pointer into a kernel buffer, that we have a kernel buffer that contains the string of that pointer, which is, C drive, blah, 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 documents. Since we read the original value into a kernel buffer, as long as we continue to use only that kernel buffer copy, userland threads cannot modify this data because this is a kernel memory address. User cannot modify that. So we don't have to worry about it changing between reads. But as long as the kernel is operating directly on a user pointer, then the userland process can have other threads running, modifying that pointer, which can cause race condition issues such as double fetch. So I kind of briefly mentioned on hypervisors, there's lots of emulation capabilities and intercepts that hypervisor code needs to pass and support in order to properly manage virtual machines and provide isolation between virtual machines. And because of this, there's a lot of attack surface between guest VMs to hypervisors. We'll touch on this a little bit more later as well. But to find out more about hypervisors, I recommend taking our dedicated hypervisor internals course or researching this as an extension to our vulnerability research course. But I will touch on it a bit more later, and we will even use hypervisors and emulators for some of our full system fuzzing in later sections. Another quick note on hypervisors. Harnessing them is usually very similar to harnessing kernel code, meaning you normally have, unless you're doing it on a live machine, you normally have it wrapped in a full system emulator or hypervisor, such as KVM or Hyper-V, or custom hypervisor code, or an emulator like Box or QEMU or something similar. But you can do it live as well. Okay, so that concludes the initial theory for us. In the next sections, we're going to dive into fuzzing from scratch a real Windows closed source service target. We're going to go through the entire process of identifying attack surface, finding the functions we want to target, doing custom harnessing, and there'll be a lot of custom harnessing techniques we'll be going through. Then we'll be turning it into a snapshot fuzzer. We'll leverage some of our custom code to emulate file system IO to get it loaded in certain full system snapshot fuzzers. There'll be a lot going on, and it's going to be very hands-on. So that is going to be the next section.